Hello, everyone. Hello, welcome to Slugs and Steins, lectures from UC Santa Cruz. My name is Mike Reapy, past president of the UCSC Alumni Council and one of your volunteer organizers tonight. With me also is David Hansen, also a former alumni counselor, and Shana Kent, executive director of alumni engagement at UCSC. Like the past few months, the organizers are going to stay on screen during the talk so that our speaker doesn't feel alone in the room, so you'll see us in the small boxes. For those who are new, our Slugs and Steins series engages a UC Santa Cruz faculty member in discussions with you, the local community of the Monterey Bay and Silicon Valley, and our extended community online, with a goal of making us all Renaissance people. We want it to feel just like you're at UC Santa Cruz sitting in class, but with a drink in your hand and without tests. Before we get started, and since we can't see you, we'd like to know where you're zooming in from and how many people are watching. Please take a moment to fill out a short poll that will pop up on the screen. See it now. We'll share the results after we've given everyone a few moments to respond. Okay, that should do it. Should see the results in a few moments. All right, looks like mostly single people, 72%, but a nice number of pairs. You know, kind of as usual, about half the audience is from Santa Cruz, but a lot of people in the Bay Area, and even a person from outside the US. So welcome to Slugs and Steins, and 2 people from outer space, maybe the space station. All right. All right, so you should have a good idea of who's in this virtual room with you now. Tonight, we will be tipping our steins this evening with Assistant Professor Leilani Gilpin from the Department of Computer Science and Engineering at UC Santa Cruz. Professor Gilpin's research focuses on the design and analysis of methods for autonomous systems. She holds a PhD in computer science from MIT, an MS in computational and mathematical engineering from Stanford, a BS in mathematics, and also in computer science, as well as a music minor from UC San Diego. I think we can say that she was busy as an undergrad, and she hasn't stopped since. She has authored or co-authored 25 well-cited publications. We will have a detailed Q&A at the end of the talk, but don't wait until the last minute. You can type your questions into the Q&A box at the bottom at any time. If you see someone else's question that you like, please upvote it, and we'll ask it sooner. In a few days, you will find this lecture on the UC Santa Cruz Arts and Lectures YouTube channel, so it is being recorded. We'll post the link in our social media channels and also the follow-up email that you got if you registered. Okay, does everyone have their steins? Great, I've got your slug, Professor Gilpin.
Great, thank you for that really nice introduction. Let me share my slides. Great. So hi, everybody. I'm really excited to be here. So I'm Leilani Gilpin. I'm an assistant professor of computer science and engineering here at UC Santa Cruz. I'm going to be talking about how we test self-driving cars and how we explain their failures. And a little bit of a disclaimer before I get started. I've had a lot of car failures. In fact, I'm a terrible driver and I get into terrible types of situations. I'm sure many of you guys have as well. This is me actually moving down to college at UC San Diego. I'm on the side of Highway 5 here. You might be able to see that there's this very strange liquid coming out of the vehicle. So we had just gotten the car serviced. This was a big drive for us. I'm originally from the Bay Area. So I went down with my mother. Because we just got the car serviced, we just got a bunch of new liquids in the car, like new antifreeze, and they forgot to put the cap on. And so what happened was the antifreeze got really hot, leaked through the vehicle, and unfortunately we had to pull over. So, you know, a lot of these circumstances that you'll see in car failures, they're very simple once you explain them, right? But they're really hard to figure out when it happens. I just, you know, I thought something might have happened with, you know, some type of different fluid. You may notice that this is actually quite a while ago too, because there's actually a call box at the side of the road. So I've been around a little bit. But there are many other different types of car failures that you may see. So this is me trying, my car got overheated. I have a Saab, which is now a rare car. And so I decided the best way to get it to stop overheating was on a desert path to just open all the car doors. That was not the right way to do it. And I ended up waiting quite a long time. And then, as it was said, I went to MIT, but I am not a snow person. And so, first time I tried to put stuff on my tires for the snow, put on chains, this is what happened. So I'm well versed in these types of car failures, and I'm going to be talking about ways that I'm trying to develop artificial intelligence and different types of tools so that I don't have to have these issues anymore, that I can have my computer just do it. And so that's what I'm going to be talking about today. So I'm going to be starting by motivating the problem. So I'll talk about how complex systems, particularly autonomous vehicles, are really prone to failure. And then I'll talk about ways that we are trying to monitor these different parts of the self-driving car to make reasonable and good decisions. So I'm going to talk about local sanity checks for vehicle perception. That is the camera on top of the car that's processing images and trying to see what's going wrong. Then I'm going to talk about the way that I'm using explanations. So I'm thinking about explanations in my research as an internal debugging language for complex systems like a self-driving car. And then I'll actually end by talking about some ongoing work. So I'll talk about how we're thinking about testing these systems and how we're developing new types of tests for autonomous vehicles that relies on some of the technologies you guys might actually be seeing in the news. So the question I'm going to be trying to answer today is, what are the explanatory AI, which is sometimes called XAI, methods for testing autonomous vehicles in safety critical situations? So in particular, I am trying to work on explanations, not just for when the car did something right, but actually when it did something wrong. So I'm going to start by motivating the problem, which is that even though they talk about how self-driving cars are a lot safer, in fact, they're really prone to failure and they fail in really complex ways. So I'm going to show here, this is the second public trial of an autonomous vehicle race car. I'm going to show this video and then I'm going to ask you guys, what do you think happened?
Oh.
Maybe I'll show it one more time. And then we're going to have a little poll. I'm very curious to see what happens. I give this question every year in my AI class, and no one has yet gotten it right. So.
This is the chance for all of us to beat your students. I think I've got it down to 2.
Okay. I'm really excited for this. This is so cool. I've never done a live poll, so.
People got it.
Wow. Okay. So lots of people think that the vision system is hallucinating and seeing something that doesn't exist. Can the audience see the poll results? Okay. So some dust on the camera lens, obstruction of the sensors, brake failure, steering wheel failure, unknown number. So some people got it right. So let me show this one more time, and then I'll go over the answer here. Let's see. Get it. So when I show this in my AI class, everybody says, I've seen this before. I've seen this in the news. It's the camera, it's hallucinating. What actually happened in this case, and I sort of hid it in the poll results. So what actually happened was that the steering component was set to NaN, or not a number. So it was an unknown number. It didn't know what to do with that circumstance. This can happen in a lot of different cases. This can happen sometimes with a division by 0. This can happen when things are set to infinity and negative infinity, and then they're never initialized. And so because the steering angle was set to not a number, it chose to take the default action, which in this case was to go completely to the right. The interesting thing about this example is that if we just had simple monitoring capabilities and explanations, I could have told you that this was going to run into an error. So we see these complex systems failing in a lot of different complex ways. And this is just one example that's actually a simple component that we would see in our own vehicles as well. Other types of failures are mistakes that a human would never make. So this is sort of the classic hallucinating example that we see in the news. So this is the back of a bus. So you see this person with a bus side ad. advertising some type of radio station, and the Tesla thinks that this is a person crossing the street. So you can imagine that the car is probably starting and stopping for this pedestrian they think that's crossing the street. But again, the big problem is that this actually affects, not just that vehicle, but also all the vehicles around it as well. There have been other types of cases. So this is a more recent case of Tesla where it thinks that it's a yellow light, but it's actually the moon. So again, an issue that would not just affect the vehicle in question here, but also all the vehicles around it. This is part of, these are specific examples of a much bigger problem. We'll talk about this a little bit later. These are called adversarial examples. So this is what happens when you add a little bit of noise or perturbations to an image, and all of a sudden it thinks that it's something else. So this is a very famous example. So this is what happens when you add just a few pieces of tape to a stop sign. So I think everyone here hopefully will agree that this is in fact still a stop sign. It's red, it has the word stop. With just a few pieces of tape, all of a sudden the vision system on the self-driving car thinks that this is a 45-mile-per-hour sign. So again, you can imagine the ramifications for that vehicle, but also all the vehicles around it. And then finally, I want to talk a little bit about the societal issues, which we'll talk about a little bit later. So many of you are probably familiar that computer vision is better at detecting faces with people with lighter skin tones than those with darker skin tones. It's been shown in these different bias algorithms. The big problem is that now this algorithm is being put on a self-driving car. All of a sudden, it thinks it's better at predicting pedestrians with lighter skin tones than darker skin tones. And so we really need to have the ability for these self-driving cars, especially in critical situations, to be able to detect their failures and be able to explain them. And so that's really the goal of the work that I do, is one, the detection of failure and error, and then the explanation. But where are autonomous vehicles right now? Well, really, they lie at two extremes. So if you look at this kind of as a graph of being very comfortable and being very cautious, what we have on one side is we have the herky-jerky ride and General Motors ultra cautious self-driving car. So what happened here? General Motors decided they wanted to be very safe with their self-driving car technology. And so their system will start and stop for anything in its way, regardless of whether that's a person or a plastic bag. So what happens is that when people are in the vehicle, they actually think it's not very safe because it's constantly going back and forth. They say, oh my gosh, this car has no idea what it's doing, even though it's actually making a very safe maneuver. So when these behaviors started coming out, a lot of other companies decided, they said, okay, well, now what we're going to do is we're going to make sure that our cars are very confident. And unfortunately, this is what happened in the Uber self-driving car fatality, which we'll talk about in a little bit. This is when Uber decided that they weren't going to have this herky-jerky behavior. Instead, what they were going to do is they were only going to stop for objects when they were very confident of what it is. Okay. And of course, that causes its own issues as well. And so, what I argue in my research is that we don't just need to have like a, one size solution. We don't just need to either start and stop for anything or only stop for things with high confidence. We need to have better common sense and reasoning. And so what I've done in my work is sort of incorporate this basic idea into how we program and maneuver with a self-driving car. And so what I create is I create architectures that are inspired by the way that successful human organizations work. And I do that with two main parts. I do that with better communication in the form of an explanation, and I do that with better error detection, which I call sanity checks. So I'm going to describe a sort of hierarchical human organization. You may argue that that's not the best way to organize a human organization, but for our purposes, we're going to work with that. So you can think about this as sort of a hierarchical set of committees. So the first thing you have is you have a hierarchy of people in charge. You have a big boss on top, you have some middle management, and then you have different groups here, different committees that are working together towards a common goal. And within those committees, you facilitate continuous interaction and communication. This is actually very similar to the way that other safety critical systems work. If you've ever seen a pilot, they're constantly communicating, saying, okay, I'm going to do this now, I'm taking this route, and everyone's constantly checking that they're behaving reasonably. In fact, that's why we have a big safety culture in airlines. And I argue that we have to do the same thing for autonomous vehicles. The way that we facilitate this is with local sanity checks. So at every time step, the different components, whether that's the vision system, the LiDAR system, even a human operator, is constantly defending what it's doing based on a set of sanity checks, abiding by rules of the road. And then when a failure occurs, then a story can be made by combining the different members of that committee's observations. This is exactly what happens when you are working and your boss writes your end report, right? Sort of takes notes of what happened in different types of communications and then presents that to other types of management. And this is exactly what we do with what I call a synthesizer. So this is a high-level explanation synthesizer, and it basically facilitates an argument. So it says, okay, the vision system says it saw that, the LiDAR system said it saw that, the sensor said it saw that, and they argue until they come up with a common belief, which is then used in a more robust way so that we can handle more errors. And I'll talk about a couple examples of those moving forward. So just with these two parts, we can actually handle a lot of the common problems that we see in self-driving cars. The local sanity checks are able to handle the long tail of errors that we see in self-driving cars. They've been shown as the trollable self-driving car. If you see one and you start to walk in front of it, it stops, then you walk back, it starts going. You can really fool it. And what I've shown here is that we can actually use these systems to justify new examples, even if we haven't seen them before. Again, very similar to the way that we as humans drive. If I'm driving around and I see a large moving object, I don't care whether that's a person or a turkey, I'm going to stop for it, right? I'm not doing the low-level object detection. And I'll talk about how we built those technologies today. Then the explanation synthesizer is really able to reconcile different types of inconsistencies amongst parts. That's exactly what happened in the Uber self-driving car accident. It's able to reconcile conflicting reasons. For a bit of a preview, and then I'll show the front-facing camera of the accident before impact. What happened was that the vision system was oscillating between a bunch of different labels. It thought that the person crossing the street, it thought that it was an unknown object, it thought that it was a tree, and it thought it was a person. And because it was oscillating between a bunch of different objects, it didn't know what it was perceiving. It actually chose to ignore the person crossing the street. However, the LiDAR system, the sensory system around the car, actually had detected the person with enough time to stop. The problem is that it's very expensive to process LiDAR. And so usually a lot of self-driving car companies don't use it at all. In fact, Tesla has said that at least a couple months ago that it was only going to use computer vision. So unfortunately, that's what happened. And this person was struck and killed. So what I'm going to do is I'm going to sort of show this example because this was a big motivating part of my research. I am going to give a bit of a trigger warning. So this is the Uber self-driving car accident front-facing camera. You will not see any of the fatality, but you will see the person crossing the street before impact. So just a trigger warning, it'll just be a few seconds. So you'll see it's very dark at night. The car is going very quickly and doesn't even slow down. Persons crossing the street. And as I said, unfortunately, they were struck and killed. So again, what's the issue with this? The issue is that the car is only dealing with the camera modality. So it didn't know how to process that the LiDAR system had detected a reasonable and a strong claim that there is a person crossing the street. And so what my solution has been, and what I'll be talking about today, is how I facilitate this type of internal communication using symbolic explanation. And so what I'm able to do is basically create monitors around the vision system, around the LiDAR, around tactics, around all the different pieces of the vehicle. This is a very simplified view for demonstration. And we're actually able to output a human language readable explanation in this form. What we find is that the best option is to veer and slow down, that the vehicle is traveling too fast to suddenly stop, that the vision system is inconsistent, but the LiDAR system has provided a reasonable and a strong claim to avoid the object moving across the street. And you can see that it's getting information from every one of the subsystems. It's not just saying that one is wrong and one is right. It's actually using that to form an explanation. It finds from the tactics, from the vehicle log, that it's going too fast. If it were to make a sudden stop, that might cause harm to the person in the vehicle. Actually, it should make an alternative plan. It finds that the vision system is inconsistent, but not necessarily wrong. It has detected something. It's just not sure what it is. But that the LiDAR system has detected something large, it's something moving, and that's something we should stop for. So I'm going to talk about how we build this technology today. And to be able to build that, we build this in different parts. So what I'm going to start with is I'm going to start by talking about the local sanity check. So I'm going to talk about how do we do error detection for local subsystems of a vehicle. And I'm going to talk about this specifically for the camera part of the vehicle. So before I get there, I have to sort of describe how this works. So I'm sure many of you are aware, but the big topic in AI and machine learning right now is neural networks and big large language models. So what happens is that we usually have a camera unit and a LiDAR unit, that's the sensory system, and that is usually located on the top of the car. Now, in more modern autonomous vehicles, there could be cameras everywhere, but there's usually at least one camera that is on top of the vehicle and it is pointing to the front. I am specifically going to talk about the camera part today. You can do a similar type of approach for the LiDAR unit as well. So this camera data is then processed as an image. So it will look something like this. Sometimes it's able to detect that there is somebody moving. It puts a box around that. And this image at every time frame is passed into some type of complex AI system, usually some type of neural network. So this goes through some very complicated set of matrix computations, like this inception network from Google. And then the output of this is a label of what we are looking at here in this bounding box. So the output could be anything. In this case, it gives some type of high-level label, like it's a pedestrian. Now, for those of you that are familiar with image processing and what's being done in AI for image detection, this works really well. Like these neural networks are able to detect people. I'm sure you played with it on your iPhone and seen that they're able to group people together. You could say that this gets about human level accuracy. So this is over 90% accurate on the labels that it gets. However, there are some problems, and I've talked about this a little bit before, but let's see the classic problem. The problem is that these neural networks are brittle. Okay, here is a classic example. So this is the classic example of an adversarial example. So I have a picture here of a pig. I hope everybody agrees that this is in fact a pig, and a very cute one at that. If I add a little bit of noise to the image, so 0.005 times this noise, and then I pass this image to the deep neural network. And I hope that all of you look at that and say, it's still the same cute pig. All of a sudden, the neural network thinks that this is an airliner. So it's fooled by these very small perturbations of pixels. And why is that the case? The reason is because what's actually happening here is that the neural network is not looking at the high-level features here, like the ears and the snout and the eyes. It's actually just looking at pixels and assigning that to the highest ranked label. And then it does a bunch of matrix computations and figures out, clusters and things. But so it can get easily fooled by different types of perturbations. Again, we saw a physical example of this with the stop sign, right? With a few pieces of tape, all of a sudden it thinks that this is a 45-mile-per-hour sign. But the big problem here is not that, adversarial examples and neural networks are fooled by these tricks. The big problem is that these have implications. If we're looking at things like self-driving and other mission-critical, safety-critical applications, like even in healthcare, these mistakes have consequences. And so we really want to monitor these systems and make sure that they make good decisions. And so that's exactly what I built in my research. I monitor these types of opaque systems for reasonable behavior. Okay. Now, why do I say opaque? The reason I say that this is opaque is because it's a very complicated system. Even in the hour I have to talk, I don't have enough time to go through what's the type of computations that are going on here. And so I actually treat this as a black box. So I treat this as some type of opaque mechanism, and I look particularly at the output. Okay, I say, okay, I've decided that this is a pedestrian. Do I have the evidence to back this up? And I build up my evidence with a little bit more information. So I build this up with a common sense knowledge base. Do I know where I am? Is it reasonable for there to be pedestrians in this area? I build that with a flexible representation so that I can represent many different types of situations in the same way. This is not just a woman crossing the street. This is a person crossing the street of average size. Then I have a set of unreasonable and reasonableness rules. You could start with the rules of the road. For example, if there's a pedestrian crossing the street, you should not proceed forward. And then I use this representation together to build up a justification of reasonableness. So this entire system is basically creating a judgment of reasonableness. So is it reasonable that I perceived a pedestrian here? And a justification of reasonableness. Why is it reasonable? Okay. And how I build that system is with something called a reasonableness monitor. So again, this takes in the output of any opaque mechanism. And we're opaque, right? So this system could say whether, the explanation that your friend is giving you is reasonable or not, if you give it the right reasonableness rules and common sense knowledge base. So the way that we do this is we represent this in a flexible way. We then have a set of rules to identify unreasonability. We use that to justify unreasonability, and we supplement that with common sense knowledge. And again, the output of this is, yes, it's reasonable because, or no, it's unreasonable because, I don't know, pigs don't fly on Tuesdays. And I'm going to talk particularly about the flexible representation because I think this is fairly interesting. And I'm going to be kind of going back a few decades and bringing back some of the work in classic artificial intelligence to be able to do this. And so the way that I represent my data for a self-driving car is I use a primitive representation. Okay. And those primitive representations are meant to encode understanding. So a lot of what you'll see in artificial intelligence is that people are using these big equations and lots of probabilities, but we actually don't process things that way. We process things at the symbolic level. And so I built on previous work by Roger Schenck in 1975, believe it or not. So I am using his conceptual dependency theory to be able to describe different types of primitive actions. So he basically said that you could represent most actions with 11 primitives. Okay. Now, I look particularly at the physical action primitives, and then I extend those for vehicles. So why does this matter? The reason this matters is because, again, I'm not concerned about the specific angle that the steering wheel is moving, right? I don't need to know if there was a small shift, but I need to know if there was a right turn or a left turn. I need to know whether we're stopping or not. And so again, I extend these for different physical actions like yielding, turning, and stopping. And using this, it's very easy to build up an explanation. Okay, so the first thing that we have to do is we have to take this natural language and parse it into this representation. In fact, this is actually the hardest part of it. So again, I'm going to refer back to the image that I showed before, so a little bit bigger. This is data from Newstein. So this is a self-driving car data set. It's made of real images, real LiDAR from an autonomous vehicle driving around. And I'm going to say that I have some label. So I'm going to say I'm able to say that this is in fact a woman and this woman is crossing the street. What I'm going to do is I'm going to take that representation, I'm going to take that natural language and I'm going to represent it into the representation I care about. So I'm going to parse this. For those of you who are computer scientists, this is a parse tree. How nice. It's actually useful for once. And then I anchor these to the common terms that we care about. So again, this is going back to the previous point. I don't care that this is a woman. I don't care that, this is a man. I don't care if this is, a group of people. This is a person. And we have certain beliefs about people. And I don't care that they're crossing the street. I just care that they're moving, right? So what this does is this makes it so that a woman crossing the street is equal to a woman skipping across the street, which is equal to a man strolling across the street, so that we can represent many different things in the same way. And that's very important, especially when we represent these with rules. The way that this is then represented is in this sort of conceptual primitive decomposition form. So there is a person, they're moving in the direction of the street, and the person doing the moving is the person. Okay, this may look very overly complicated, but again, this accounts for most of the behaviors that we see of pedestrians crossing the street. So it makes it a very powerful representation that we can use. Now, the key point here is that if I know that there's a person crossing the street, I have certain reasonableness rules attached with it. In fact, in this representation, I can tell you what's reasonable and not reasonable. So let's talk a little bit about that. And again, this is a little bit of logic and stuff. So if this goes over people's head, I'll talk about it in plain English. So what I can say is that if I know that something is moving, okay, if I perceive something moving, then it's reasonable if the actor that is doing the moving, okay, whoever is doing the moving towards the location, either it has the property that it's adamant, so it can move on its own, and it's located near the direction it's going. Okay, then I can say that this specific primitive is reasonable. And in fact, if I look at a particular image, if all the different movements that are occurring in that image are reasonable, then I can say that the perceived frame is reasonable. And that's really the key point here, is that we can say whether movement is reasonable or not with just a countable set of rules. All we have to do is represent that in a common form. And in fact, that replicates exactly what I said before, which is that when I'm driving, I don't care whether that's a turkey, a squirrel, it's something that's moving, and therefore I should stop for it. And we're encoding that now into a self-driving car. So let me show you some results of that on real data. So again, if I actually look at what this looks like, if I'm to actually process this data from new scenes, right? So a lot of people will process this and use very complicated mathematics and machine learning. And the type of data that we really see from this is it's very noisy and it's really hard to interpret. So, you'll see the sort of token, how visible it is on a scale of 1 to 4, but really all that we need here is just the category name. And then we can combine this with a common sense knowledge base, like something like ConceptNet, to get the right information that we need. So another contribution of this system is being able to find the right context-specific common sense. Okay, so lots of work in classic AI has been about aggregating common sense knowledge. The big problem, again, is that it's unorganized and a little bit noisy. So let me show you what I mean. So if I look up an adult, so I say, okay, I know that I've seen an adult, you'll see that an adult is capable of helping a child, dressing herself, working, drinking beer, signing a contract. That's not really what I'm looking for when I'm trying to do this for a self-driving car, right? But I am interested in other types of properties, like an adult is a type of animal, and animals can move on their own. And so part of our system is actually weeding down or filtering this common sense knowledge so that we get the right type of propositions that we need to explain. So we need that an adult is a type of animal and animals have certain properties. And we need that an adult is bigger than a child. We need a way to compare it to different sizes of objects. And so using that, we are able to actually monitor these systems and output a judgment and justification. So let me show a couple examples of that. So again, using my reasonableness monitor here, if I pass this in as a human, pedestrian, adult, I say that this is reasonable, obviously, because it's an adult, it's typically a large person, they're located walking on the street, so we get context from the scene, and its approximate dimension is approximately the correct size in meters. Okay, now we can also scramble this and we can say, okay, well, if this was something like a fire hydrant, it would say that, well, that's clearly unreasonable because it's actually something that's moving. So with these types of systems, we're actually able to deduce this. And the big part is we're actually able to do this in real time because we have such a simplified representation. So now I'm going to tie the system into a bigger system, into full system design. So how do I use these explanations in a self-driving car? So I've shown how we can do this after the fact, but how do I do this so that we don't get into the types of accidents that I've shown before? And I'm going to talk about how I do that with explanations as an internal debugging language. So what I'm going to talk about now is actually my PhD thesis work. So I'm going to go through it in about 6 slides. So again, very highly simplified. So my idea was that we should use an organizational architecture to deal with self-driving car failures. So again, this is a very simplified view of a self-driving car. Obviously, there are many, many different components, and this really relies on a few different things. So I put monitors around everything. So I showed you the reasonableness monitor in the first part. I just encapsulate each part of the system into a reasonableness monitor. You see the sort of dashed lines around each one of those. Then I have a explanation synthesizer. Basically, it facilitates an argument amongst parts. It does that to deal with inconsistencies. So if the vision system says it saw something, but the LiDAR system says it didn't see something, how do they argue and figure out who's right and who's wrong, especially in these critical situations? It does that by building an argument tree, and that argument tree can be queried for support or counterfactuals. That is extremely important. And the reason that's important is because when these cars get into accidents, we want to know why. So what I can do is I can play with this system and say, you know what, actually, if you didn't detect that that person was a tree, this wouldn't have happened. I'm able to do that dynamically with this architecture system. And I call this anomaly detection through explanations. That's the title of my PhD thesis. If you have a spare 5 hours and really want to read something, I well, I don't know if I highly recommend it, but some pretty interesting findings. And I'm going to give the highlights of it now. So the real key here is that this is an architecture, but it also does reasoning. So you can put this architecture on top of your self-driving car simulation, on top of your autonomous vehicle, and it will detect and explain errors for you. It does that in three main parts. I'm only going to talk about the third one today. So the first thing it does is it gives it a common language. I use a symbolic qualitative description. All that means is it's a description of the first derivative. So it says whether it's increasing or decreasing or staying the same. Then I use reasonableness monitors, which you guys saw before. I take those descriptions and I put that into a local reasonableness monitor. Then I get a justification, a small explanation of what happened and why. And then I will use the synthesizer that will reconcile the inconsistencies between the monitoring outputs. So I'm going to particularly talk about part 3 because I think it's the most interesting part. And I'm going to describe particularly how we reconcile these inconsistencies between the monitoring outputs. So remember that I alluded to the fact that the synthesizer, it actually is meant to deal with inconsistencies. So it does that by building an argument tree, which can then be queried for support or counterfactuals. But you need to tell it what to prioritize, right? So we have to give the synthesizer a priority hierarchy that can then be turned into abstract goals that we have to meet in order to be safe. So we do have to give it a set of priorities. And I think this is where a lot of questions will come from. And I think this is where we'll have a lot of discussion. So we define this in terms of a 4-part hierarchy. This is inspired by the literature. I am particularly going to be talking about passenger safety. Now, that's a historical name. That doesn't just mean the passenger in the vehicle. That means also the neighborhood, the vicinity around the vehicle as well. You define that radius. Okay, so if you define your radius as very far, then it's going to sort of start and stop for everything. If you define it a little bit closer, then you'll have a little less sort of shaky behavior. But you need to define what this priority is. And so one of our definitions of safety, and there are several that have to be met in order to make safe decisions, is that a passenger is safe if the vehicle proceeds at the same speed and direction and the vehicle avoids threatening objects, right? So that just means that you're driving around, you're not making sudden stops if you don't have to, and you're basically avoiding any type of threatening object, whether that's a person crossing the street or that's a large box in your way. And so that's really how we define passenger safety. Now, a little bit more about the priority hierarchy. So many of you are probably thinking, oh, this looks like the trolley problem. It could be, right? So what you could do is you could write out all the priorities that you want, whether that's, that you want to make sure that, the 2 people on the right side are safe before the 2 people on the left side. And you can play with that and you can actually play with this architecture. We particularly defined it to be very vague and very high level so that we would avoid the ethical types of questions, but there's a lot of future work that can be done with actually looking at this for ethical implications. So let me talk a little bit about how that works. And we're actually going to get into the tech here. So I'm actually going to show how this is represented in code. And for those of you that don't like logic, well, close your eyes, here it is. So we represent this in a first order logic. I'll describe this at a high level. So this is just saying if you have 2 states, so you have X and you have T, which directly follows it, then you need to have that both of them are going at the same velocity. So your same velocity in state S, same velocity in state T, and you avoid threats in either one of those states. So that just means that at every time step, you're looking at the previous time step and the current time step, okay? If we have that, then we can say that the passenger has the property that it's safe. Okay, so we still have to define what a threat is. There are many definitions of a threat. In this case, for the particular example that I've shown with the Uber self-driving car accident, it is a threat if it is an object, it is near, and it's moving. So if it's a large object, it's located near where the vehicle is and it's moving, which again, the same example that I said before. When I'm driving, I don't care if it's a turkey crossing the street, it's large, it's moving, I have to avoid it, okay? So that means it's a threat, and as long as I avoid it, then I have the property that I'm safe. So let's actually talk about how that is represented. So this is a small snapshot of the type of data that you would have in a qualitative symbolic system. So this has been translated all to symbolic triples. And when I actually run this code on the Uber self-driving car accident, what happens is that it doesn't find that the vision system is wrong. And that's a really key point. What it finds is that another modality, the LiDAR system, has actually detected a threat. And because it's detected a threat, it should be avoided. And that's how we get to our final explanation. And I think that's really a key point, because a lot of what's being done in artificial intelligence right now, everything is a confidence, right? Oh, I'm 80% confident, 95% confident. And when we're in safety critical situations, we're not thinking about confidence, we're thinking about common sense. And I think that that's really critical to think about here. And we've encoded this in those types of systems. So I'm going to show you guys a little bit of an example of how this actually works. As I said, you could actually run this on a real self-driving car, and we've done that so far in simulation. So this is a simulation of the Uber self-driving car accident. And you'll see that the car actually takes an alternative action. So it starts, going down the street. You'll see here that there's a person, they're crossing the street, and the car swerves out of the way. So for those of you that were really paying attention, you may come back and go, oh my gosh, Professor Gilpin, I saw that it was a person and they were carrying a bicycle. Unfortunately, in the simulations that we were looking at, this is a simulation in Carla. In this version, it actually didn't have the capability for a person and a bicycle to be crossing the street at the same time. So what we did was, after the fact, we added a little bit of noise. So it actually was the right shape of a person with a bicycle crossing the street. But we think it's, very exciting that we can actually do this type of detection in real time. And in fact, we actually get, a fairly nice explanation, again, looking at it at each time step. So talked a little bit about how the tech works, but I haven't talked about how do we know that it's right. And actually, this is a really big problem. So it's very difficult to test autonomous vehicles. And I'm going to talk about some of the work, again, that we're doing in my group to test them by augmenting different types of data sets. So what is our vision? Our vision is to have these real world adversarial examples. I showed the pieces of tape on the stop sign. I showed the pig that's on an airliner, but we actually see this when we're driving around as well. It's a little bit difficult to see because this was taken on a phone camera. This is a truck. It's classified as a truck with 0.46 accuracy, and it is a truck that is carrying traffic lights. And the traffic light is also fairly confident at 0.53. So what happened? A self-driving car saw this and it stopped for it, right? Thought that it was a traffic light. We want to tell the self-driving car that this is actually something it shouldn't stop for. What we actually want to do is we want to create a sort of anticipatory thinking layer. We see a lot of these instances in the real world. I'm sure you guys have seen, hilarious instances when you're driving around. And what we want to do is we want to use our explanations. So explanations of what we see and why they're, funny or unreasonable, to motivate data collection and data augmentation and data creation for testing self-driving cars. So we want to take this explanation. This is not generated by any of my systems. This is, target explanation that we would want, annotated by a human, basically saying that the lights are moving at the same rate as the truck. Therefore, this is not a traffic light that you should stop for. And this is part of a much, much bigger problem. There is just lack of data and challenges for autonomous vehicles, especially for failure and error detection. Why? Because the current challenges are targeted at optimizing a mission trajectory and not safety. The data is hand curated. If you look at data from news scenes, if you look at this image, every part here is labeled. There are bounding boxes around the people in blue, around the objects here, around the vehicles in yellow. This is the ideal data set. But again, when we're driving around, there's fog, there's noise, there are cars parked in different directions. So this really isn't representative of what we would actually see just driving around. And again, we don't have a person, well, sometimes we do, but in general, we don't have a person next to us saying whether these labels are right and whether the bounding boxes are tight. The other big thing is that getting failure data is very difficult. I can talk at length about that. One, it's unethical to get. I can't just, tell people to drive into bad situations. I'd really like your data, right? At the same time, a lot of the simulations that we've done are just not realistic. Some of you may notice in the simulation I showed, the car kind of swerved out. The physics are not exactly perfect when we look in simulation. So we have this interesting issue, which is that we want bad situations because we want to be able to explain them. But at the same time, the types of simulations where we can play with it, they're just not realistic. And so what we've done, and this is work with my master's student, Shinjia, is that we've created this type of anticipatory thinking layer for error detection. Shinjia came to me when he was starting his master's, and he was saying, I think I figured out your problem. There are entire people on Reddit that create a thread called Idiots in Cars, and they generate all these wonderful trajectories. They take videos on their car and show people making bad maneuvers. And he said, I wonder if we can do that. Can we learn from these threads of people saying, look what I saw on the road today? And can we do that and augment existing autonomous vehicle data sets? And the answer is we can. So we took some existing autonomous vehicle data sets, we took some of these crazy maneuvers that we saw before, and we take the vehicle out of the original scene and then we paint it in, making these dangerous maneuvers. Now, this video is a little bit downsampled, so you may see that the car looks a little bit unrealistic. But in general, this works really well. And the big key point here is that the distribution of the data is the same. The distribution of the data, we haven't added any noise, right? We're still using the same vehicle, we're just painting it in a different direction. So there's no sort of classic adversarial example in this case. So how is this done? Just very briefly, we identify the car that we want to maneuver around in a dangerous scene. And then we add the car back in, we remove it from the image, we what is called de-render it from the image, and then we add in a bunch of different vehicle primitives. So everything from a sudden stop to a sine wave to cutting in left and cutting in opposite. And then we create a new data set, which has the original self-driving car data set, as well as a bunch of new dangerous scenes. The interesting part of this is that actually this ends up not being really an AI problem. It's actually a computer computational geometry problem, which is that you have to then paint the trajectory in the frame of reference of the car. So it's actually, I think it's a very cute sort of example. This goes back to some of my earlier work when I was doing computational mathematics. So I feel very lucky that I got to sort of go back to basics there. And let's see a few more of the results. It's a little bit difficult to see here, but we have everything from exit parking, so a car that was parked all of a sudden just exits out, cutting in opposite, which we saw on the previous slide, general cut-in behaviors, the slalom lane change, that's sort of the sine wave behavior that you saw, and sudden braking. And again, this works pretty well. We're currently applying this methodology to a lot of different data sets. We've shown it here for Virtual Kitty. We're also doing it for Waymo, which is actually photorealistic scenes. The only difference with that is it takes a long time to de-render, take the vehicle out of the scene because it's so realistic. But yeah, we're very excited about this work, and we think that this is going to be sort of a new benchmark for safety critical systems. So in conclusion, I talked about a bunch of things today. So I started by motivating the problem, which is that self-driving cars are prone to failure. And this is a common issue of many different types of complex systems. And I motivated that with the Uber self-driving car fatality, where unfortunately a pedestrian was struck and killed because we were relying too much on a local modality. And it was a situation that we had not seen before. I then talked about how do we develop local sanity checks for vehicle perception as one type of solution. And then I talked about how do we put that into full system design, so as an internal debugging language for a self-driving car. And then finally, I talked a little bit at the end here about ongoing work in testing autonomous vehicles by augmenting different data sets. And I sort of inspired that by some of the crazy behaviors you may see online. You may think that people who are sitting on Reddit are, doing ridiculous things all day, but actually they're helping feed our research. So with that, I thank you guys for your attention, and I'm happy to take questions.
Marvelous. Thank you, Professor. So we have many questions. We'll start with Jeff. How can you incorporate cultural behavior into autonomous driving? For example, in Vietnam, it is very common for people to just walk into traffic to cross the street. It is basically up to the driver of the vehicle, automobile or motorbike, to avoid hitting the passenger by driving in front or behind.
Great question. We are working on that. Unfortunately, I didn't have enough time to go into that. One of my other projects is on learning driving behaviors from driving handbooks. So I don't know if they still do this now, but at least, again, when I learned how to drive, and I'm still a bad driver, you would go to the DMV and you would get this document, like a big textbook. I don't know if they still give it now, it's probably online. But you'd sit there and you'd memorize it, and then you'd take some tests, and then you'd go out in the wild and they'd make you do a driving test. those have a lot of cultural behaviors written in, and we've actually found that. We've looked at it for, we've looked at these driving handbooks for 3 different countries and 26 different states. And we've seen that you actually start to see through that text, different types of behaviors come out. I'll give you an example. So again, I went to grad school in Boston. I hope I don't offend anybody, but Boston is known for its aggressive drivers. And we actually found more aggressive language in the driving handbook for Massachusetts than that of California, which is, you know, quite a shock to us. But we're actually very interested in doing this for international manuals as well. The team, we have a couple students of Indian descent. So they're looking at parsing out a couple different language manuals. But so that's one way that we're thinking of, but also you can learn these behaviors through experience. We haven't gotten that far yet, but right now we're working on the driving rules.
Great, thanks. And I think you'll find there's a lot of questions coming in, you know, of self-driving cars in general. So you can see I think there's still a lot of distrust out there.
Okay.
Technology.
But I did my job.
Yeah. Ryan asks, is it possible to create different states for the car? For example, if visibility is low, the car would enter a more defensive state by predicting possible obstructions and be more likely to stop or take evasive maneuvers in case it finds an obstruction at the last second, like in the case of the autonomous Uber car crash. So
yeah, absolutely. So the answer is absolutely. There's a problem though. The problem is, and I didn't get into it, the problem is with the handoff. And we've actually seen this happen before, which is that a lot of autonomous vehicle companies, and another autonomous vehicle agent you can have is yourself. And actually that's a big handoff issue too, but they'll have several different agents. And when they switch between these agents, there'll be a big pause because it takes a while, it has to change different parameters. So what they've actually found is even though you can have multiple agents in the car, the problem is that switching off with them in these time critical situations, it actually doesn't work as well. That's actually something I worked on when I was working at Sony AI. We were working on these, I was working on Gran Turismo. I don't know if anyone's familiar. It's a racing game. And we'd have different agent behaviors. I can say this now because it's published. We had different agent behaviors for the straightaway versus the turns. And we would have to preempt the turns. Otherwise, the trade-off, it would start the turning behavior way too late. So the short answer is yes, but we need better ways to sort of transfer between these different agents. And again, we see the same thing. I don't know if people have encountered this in, well, I guess the semi-autonomous vehicles that most of us all have, which is that sometimes the car will ask for help or it'll say to hold the steering wheel. And it's usually a little bit late before you realize that you're like, oh, yeah, sure, I'll hold the steering wheel. So there is this sort of lag that causes some issues, but I think that's a very interesting open area of research.
So here we have a challenge. How would falling trees be considered under the language model of reasonableness? So
let me see, could you repeat, you said falling trees?
Falling trees, yes.
Great question. There is always a corner case. So I get falling trees. The big one I get is police officers. So if there's a pedestrian in the way, you should stop. What if it's a police officer that's waving you through? Well, then you should go. So there's always a corner case to these types of systems. This is a well-known issue, and a lot of what I do is classic AI rule-based systems. For the falling tree example, I would say that a lot of that relies on your common sense knowledge base. I mean, maybe you're alluding to Highway 17. I think many of us have nervously drove that in a windy weather and knew that the tree could go at any point. But again, I think that that's a common sense behavior. We know that if it's raining, it's windy, and if we're on Highway 17, that tree might be moving. In fact, it might be moving right in front of you. So I think a lot of that has to do with how you're using your common sense knowledge base and what type of additional context you have. I think that that's something that, you can always make an exception to a rule. And once you make one, it becomes a slippery slope. So I think that that's an issue of aggregating better context.
Okay. We have a comment from Todd. He's watching here. He's asking if you could remove your slides, because I think we're getting freaked out by this driver.
Oh, sorry about that.
Perfect. Thanks, Todd. I wasn't paying attention either. We have a number of questions. It's actually similar to the one I just asked last time, right? Like, what about weather? I see like Ryan, I think there's a couple here, like, different situations, night versus dark, good weather, rain, snow, lightning, hail. Are those all different adversarial conditions you need training examples for? Or?
Yeah, that's a really, it's a really tough question, again, for a couple of different reasons. One is that the last thing you want to do is be testing your autonomous vehicle that costs tens of thousands of dollars, maybe even hundreds of thousands of dollars in these weather conditions. That was actually a big issue when I was in Boston. We had a team that was actually working on the hardware, and they were they didn't know what it was going to do in the snow, and it couldn't get into an accident. And the other problem, again, the simulations are not as good. So, handling weather is a really big issue, especially where we live in Santa Cruz. I can't believe we saw snow here. I almost forgot what to do. So, a lot of what people will do is they, again, will have a rule set specifically for these weather situations. Now, the difficulty is recognizing what weather situation you're in, right? If you're thinking about this again at the image level, what's the difference between rain and snow? Like, they look the same to a camera. What about hail, right? There's a sound to hail, but again, if you're taking a picture, you see a bunch of white dots, they all look the same. So it really is, it's a very difficult data fusion problem. A lot of self-driving car data sets, they'll have a weather, I think you might have seen it on one of the slides, they have like visibility or weather. So they'll actually label that data for you. But again, in the real world, it's very difficult to do. I know that there are people, actually colleagues of mine at Santa Cruz, that are working on ways that we can connect cars. They're already connected, but connecting them to like weather apps so that they can automatically tell whether it's raining or snowing. Of course, they're not perfect, but that's one type of solution. But yeah, it's extremely, extremely difficult. And again, consider us, like, in a rainstorm, I'm a terrible driver, but I never know what to do. So I think that those are going to be the really, really difficult things, especially for autonomous vehicles moving forward.
Okay, so Benet asks, in failure examples, were system logs designed to record enough information to do complete forensic diagnosis?
So great question. So I don't know with modern vehicles, but I can speak from about 5 years ago when I was looking at these for my thesis work. So since the 90s, and I don't know if this has changed, because again, I'm talking about cars from 2018 now, all vehicles had to have a version of CAN, that is Controller Area Network, and that records all the different subsystems of the vehicle. So for example, if I put my window down, that's being written to a log. I don't know why, but that's how it works. So every component is connected to CAN. I don't know about autonomous capabilities, because at the time when I was working on it, people would put a camera on top and they would just connect it, not connected to the network. So a lot of the car data is recorded. So any mechanical part of the vehicle is recorded, gas, brake, steering, that is all recorded. But I believe that the multimodal information, the vision and the LiDAR are stored separately. And in fact, that is reflective of the self-driving car data sets that we see. But most of that data is recorded. Now, I can't speak for sure. I don't work with any car manufacturers right now. I think there's good reason for that. I would detect all their errors and failures. But think about when you have the diagnostics tools in the vehicle, you plug them in and then they give you a code. That's essentially the same thing that we're doing, just for a very long time trajectory.
Okay, thanks. Just a reminder to everybody, we've got a lot of great questions coming in, keep them coming. Also, browse through the questions and give us some upvotes, right? You can help us decide what order to ask these questions in. Rao says that, granted, it is not possible to build a 100% safe system. What legal framework do you foresee developing to deal with accidents caused by self-driving cars? Do you see a failure where software can be convicted of manslaughter, or where software is acquitted of any wrongdoing for killing a pedestrian?
Oh, wow. What a great question. And I will start by saying I do not have any legal training, although I sat in a policy lab when I was a student. And if anybody here has legal training and is interested, I would love to talk to them. That's a really difficult question. I wish I had a good answer. I mean, I think that we have to have vehicles be able to explain themselves, especially autonomous ones, if they're going to be holding people in them that could get into accidents and cause fatalities. I mean, I will use the analog. I'm sure you guys all know. I mean, I just showed several of my accidents. You get into a car accident, right? You get out of your vehicle, you provide an explanation, a testimony, right? An independent observer takes that down, hopefully independent and third party, and then someone else gives their testimony, and then there is a adversarial proceeding. They figure out who's right and who's wrong. Right now, the capability to do that is nothing. The autonomous vehicles that we have now don't give any type of evidence. In fact, if you look at the the report after the Uber self-driving car fatality, I mean, it took months, and I think the eventual report was that it was the safety driver's fault, but they were supposed to be distracted, and so Uber was not liable. And I don't think that's exactly right. Again, I'm not a legal expert, but I think that we have to have, if we're going to put machines in charge of human level decisions, then they have to be able to testify and explain like people do. So I think if we can work on creating that technology, then we can also work on the legal framework to reflect that. But we don't have any of that right now. We don't have any explanations except for some of the work we're doing in my lab, and we don't have the legal precedent as much as I am aware.
So this segues into Marcelo's question. Impressive work, congrats. Interpretability, especially using natural language, could also mean liability to car or autonomous system makers. How is your research being accepted within the industry?
Oh, what a great question. As I said, it's not. So there's a couple of reasons for this. So again, my thesis work was funded by the Toyota Research Institute, which has now stopped working on autonomous vehicles. Maybe it's due to me, maybe it's not. So this is the Toyota Research Institute, not Toyota as a whole. I think that it's very difficult. So I can give the analog. So, we were promised a lot of data when I was a student, and I didn't get any. And I think I know why, right? Because if there was a headline that said MIT engineer finds flaws in car manufacturer name, that's terrible press. So I can see why these car manufacturers would not be necessarily excited to work with me yet. I also think that the bigger problem is that, and this is again my personal opinion, there's not a safety culture around autonomous vehicles yet. The culture around autonomous vehicles is innovation and being first to market. And so safety is maybe number 2 if we're lucky. So again, it's not a huge priority. And I think we've seen this in a lot of different applications. In fact, I'm very inspired by a lot of the work that goes on in airplane monitoring. In fact, a lot of these techniques are the same techniques that they work on in airplane monitoring. But again, it took a safety culture for that to be accepted. So it hasn't been accepted yet. I think that a lot of people are excited about it from academia. But if anybody knows any car manufacturers that are interested, I would love to talk, and I would not publish without their consent. So.
Fantastic argument and advertisement. Let's hope somebody's listening and takes you up on that. Here's an interesting question from Ryan. Right, this is not theoretical. Self-driving cars have been approved in some places. San Francisco has taxis. There's like autonomous pizza delivery truck cars. I don't know, I think Austin has some as well. So these have been approved, right? What kinds of tests do you have to pass in order to make a self-driving car street legal?
Ooh, that I actually don't know. I mean, I think it's so one is, I will say again, my humble opinion, this is Leilani's opinion, not as a representative of different universities. I mean, I think it's incredible. I was shocked. I mean, a lot of my friends work at Waymo, and I was like, really? They're letting you guys drive? Oh my goodness. I don't know what they have to pass. But I'll tell you, they didn't pass a driving test, right? All of us who drive cars at one point had to sit there with an expert and prove to them in a vehicle that we could do it. And I have not seen a driving test for self-driving cars. Maybe there is one. There's a secret society that no one tells me. But so short answer, I don't know. And I think it's, really incredible. I would also say, I do know, I cannot share, I know a little bit about how a lot of these systems work. And again, I think that they're not ready. Like, I really don't think that they are. But, they're being used for short distance transportation. I think that, the average amount of failures there is very small. So.
Just curious though, like, where is it being approved? Is it sort of like low speed, like city traffic? It's a little bit safer.
Yeah, I mean, God, it's I wish it was like Who Wants to Be a Millionaire? Could we phone a friend? I I have a great expert I can ask. I think it's low speed. I have seen it in high density. I have to say there are remarkable videos. Again, I have a lot of friends that work at Waymo, so I might rely on that. Where Waymo is able to cut through these different like parking maneuvers in San Francisco. I mean, I was blown away. I think that they're doing a remarkable job. But again, it's one city. And, if you know San Francisco, right, it takes a lot of training, right? But, I grew up in the Bay Area. If you know San Francisco, you can drive through it pretty easily at a slow speed. So maybe not. Even I can disagree. But, there's going to be traffic on 19th Avenue, right? Like, the usual. But yeah, I don't know. I think that it's low speed. I think that it's only certain cities. I haven't seen any freeway driving. And again, the one thing, I sort of told you guys before, but I don't know what these companies are doing. None of their algorithms or their data sets have been open source. Waymo has released a small data set, but not, of course, they're encompassing the other big one that they use at their company. So a lot of the answers to these questions are, I don't know. I wish I knew. And if anyone knows, let me know.
So there's no one developing a cross-continental I-80 truck system that you're aware of?
There is it, oh gosh, so I apologize in advance. I think it's Aurora is working on an autonomous truck. I don't think that they are deployed yet, but their specific application is long distance trucking.
Okay. So Justin asked, was the outcome of the Uber pedestrian incident, and he'd actually thinking broader, maybe scenarios of this type, was that any worse than if a human driver were in control of the vehicle? So I think he's thinking probabilities here.
Yeah, I mean, that's an interesting question, right? So I think you can sort of take both sides of it. So one is that, it was dark, the vehicle was going fast. It was like 2 or 3 in the morning. Like, there's no reason to think that somebody would cross the street. So, I could see, unfortunately, that being done by a human. I also think that the minute that they were shown in the headlights, if it was a human, they would have made a sudden stop. And if you saw the video, I mean, maybe there's a tiny bit of braking, but I saw, that car did not slow down. So, do I know what would have happened? Maybe they would have gotten hurt, but not, maybe it would have been fatal. I don't know. I mean, I think the biggest difference again is the liability. Like, I can tell a symbolic story. I can tell you, oh, I was driving really fast. I was a little bit distracted. It was very late at night. And this person shot out in front of me and I slammed the brakes as fast as I could, right? The big difference is the autonomous vehicle can't do that. It doesn't have any recourse. And it does if you spend about 6 months, digging through the logs to try and find it, but by then it's too late, right? So, I do think that a lot of these incidents that we see are ones that would also be tricky for a person. I don't think, again, that we're going to have a no accident autonomous vehicle, But at the same time, a lot of the scenarios that we see are ones that could be less fatal and definitely at some points avoidable.
Okay, we have a pretty technical question from Anthony here.
Mhm.
Are the reasonableness monitors that you talked about, or the explanation synthesizer, are these machine learning systems in their own right? Are they high-level models for system design?
Yeah, that's a very good question. So there is the capability of these systems to learn from their environment. We actually don't do that, and I'll tell you why we don't do that. The reason we don't do that is because if you learn from your environment, so in machine learning, you're learning from data. What happens is then you create an exception from every rule. And we actually deployed this on a small autonomous vehicle. We had to drive around and make a bunch of anomalous maneuvers. And what happened was that the rule set went from, for the small autonomous vehicle, 8 rules to hundreds in a very short amount of time. Because again, it didn't know the type of abstraction. So you have to actually tell it what to learn. So right now, it is a completely logical reasoning system with no machine learning. So it uses, classic tools from logical reasoning. So resolution, unification, things like that. We'd love to incorporate machine learning, and we're working on that for learning the rules from experience and figuring out which ones are very critical and which ones are not. I'm actually looking for a student to work on that. We haven't done that yet. So right now it's basically a model with logical rules.
See, David?
Oh, sorry.
Okay.
Yeah, teenagers. Could you study the errors of teenagers as examples? Fill your database with teenage activities.
Ooh, that sounds great. There are issues. We actually thought about this. There are issues with people under the age of 18 driving. So the answer is probably not. We might be able to get anonymized data. But I think you're absolutely right. I think looking at new drivers is absolutely the key, but it's very difficult to collect data, especially car data that contain minors. But I think that's a great idea.
For privacy reasons.
Yeah, for privacy reasons, for legal reasons. Actually, the big one is actually for insurance. Because a lot of these cars now, I think they've gotten rid of them now, but they used to have you could put an insurance dongle in your car, and then if you had good driving behavior, they would take a little bit of money off your insurance. I mean, of course, it did just the opposite, right? You make one bad maneuver, and all of a sudden your insurance goes ways up. So I think one of the issues would be if we collected that, the insurance companies would go hog wild trying to collect that data because they could figure out which families owed more money. Again, my humble opinion, but.
Okay, Chris is asking, do your models maybe incorporate the laws of physics?
Yes, they do. There are entire great question. So there are entire qualitative physics models that we use to represent these different changes. That's not as exciting as showing the pictures and the videos. That's a little bit boring math, but yeah, so we have those qualitative physics models. Again, they're finicky because a lot of the work that we look at and a lot of the data is in simulation, so it doesn't, some of the physics is a little bit off, but that's actually why we use qualitative change. We use qualitative change because it's a little less noisy than you would see with just sensors.
I wonder if we have the processing power to really do that to its potential.
Yeah. I mean, now we have a lot of it. A lot of the driving games actually have remarkable physics again, but the issue is the types of games we see, they're either racing or things like Grand Theft Auto, and I mean, they're kind of at two extremes, right? So we need something that's kind of like normal driving with good physics.
Ryan, so building on sensors, Ryan asked, could you use 2 adjacent cameras to mimic human eyes and perceive things like depth rather than relying on LiDAR?
Yes, there is an entire area of research that my colleague Sihong Zi does, not me, on a bird's eye view, which is exactly this idea where you take a bunch of different cameras and you sort of project down like a top-down view of the vehicle, which is really cool. And yeah, then you don't have to rely on LiDAR at all. Again, the issue is kind of with detection, like, again, you create a new problem right now. If you're looking top down, like, what about things beneath the car, or things that are not necessarily at sort of the level of the bird's eye view that you're looking at. But yeah, that's a whole new, I guess it's a newer area of research that a lot of people are thinking about.
Okay. Oh, I love this question from Kurt. Thank you for this. What about Asimov's 3 laws? And I had a similar question, right? How do you prevent this machine from, killing a human on purpose? Or what do you do, like, if the machine has to choose, like, I'm going to hit the thing in front of me, or I'm going to slam on the brakes and let the car behind me hit me, right? Like,
oh God, I know. So good point. You may notice that some of the priorities are very similar to Asimov's rule. So again, there's reasons for that, right? That's largely what's written in the autonomous vehicle safety literature. It's a really difficult question, right? What would we do in the same situation, right? If we see something, like, I think our initial reaction is not like, okay, I got to save myself first, or, oh gosh, I have to save the person in front of me first. I think that we make the best decision that we can in that situation. Usually we slam on the brakes. And so I think that a lot of those they're very hard to represent. Again, that's why we represent these things as threats, and we just say, okay, we got to stop or make alternative turns for threats. I think that there are some ways to learn those preferences from behavior, which maybe is, I don't know if that's good or bad. But I think that those are really, really hard questions, and there are, entire subfields of science fiction that are dedicated to that. The tough thing that comes into place here is actually, you see this more in personal robotics, which I don't work in, but you may have seen that there are now these mall robots. At least they have them in Palo Alto the last time I was there. And the mall robots are really bad, and they'll sometimes run over children because they don't really see what's in front of them. I think that's something we really have to be concerned about. I think with the self-driving cars, especially in this fight or flight, when you're going really quickly, like, you just have to take the best decision you can in that moment.
do you collaborate with like ethicists or philosophers?
Yeah, absolutely. When I was a PhD student, I sat in the policy lab. I talked a lot to people in the philosophy department. I work very closely with an AI ethicist at Imperial College. So I'm always thinking about those types of problems. The difficulty is the representation. So in ethics and in philosophy, you'll have this like representation, and that's not the same that we have in computer science, right? In computer science, we have probabilities, and that was the translation process is very difficult, and that has to all be done by hand. So I do work closely with them, but a lot of times it's, there's a big abstraction barrier between like what they want and what's possible on the types of systems I look at.
So we're coming quickly towards the final question here. Maybe we'll have at least one more, maybe two. So Fedor asks, based on what you were saying earlier, again about these cultural differences, would you expect a different model behavior based on which state or country the autonomous vehicle operates in? Would you expect Boston autonomous vehicles to operate differently than Santa Cruz ones?
Oh, absolutely. I hope so. I mean, I'm sure many of you guys have had this instance happen before where you drive in a new area. I mean, again, I had that when I went in Boston. I'm lived in a lot of beach towns. I kind of drive, I very slowly go onto the freeway. Oh my goodness, I got honked at, like everyone's yelling at me. I mean, I had to learn that Boston drives differently. And the same with autonomous vehicles. I mean, unless there are specific places where autonomous vehicles drive and they all have the same behaviors, and then there are location specific roads where locals can drive. Maybe that would be an exception, but no, I think absolutely. I have the same thing when I drive down to Southern California. I switch from Santa Cruz driver to like LA, I'm going to cut across 5 lanes kind of driver. And, we all do that. And if you don't do that, again, you get honked at, you get yelled at, you get terrible hand signals at you. So I think autonomous vehicles, at least while we have human drivers on the road, they're going to have to do the same.
Okay. Yeah. Thanks for the time check, David. We've got about 5 minutes. I want to see a flurry of upvoting here. We've got 26 open questions still, and we're not going to get to them all. Everybody can help us pick maybe the last one or two. A bunch of questions here, actually, like from Ibukun or about animals, right? What about animals instead of people, and does that change your decisions, right?
Oh yeah, I mean, animals are large moving objects as well. They are also threats, but they have different behaviors. I think that's the biggest thing.
Mm-hmm.
I mean, again, I will use the Turkey Santa Cruz analog because I have never seen an animal walk so slowly across the street. When I see a flock of turkeys coming, I know it's going to be like 2 minutes. Like, gosh, they just take forever. But again, we have to tell the self-driving car that, right? Like, we have a certain expectation that when a person crosses the street, I mean, at least like when classes are out, right? That is, again, a different type of behavior that we have, and that will be represented in the common sense knowledge base. So those are absolutely part of the system, right? Now, which, at what level do you kind of represent that? I don't know. Because, different animals have different types of behaviors, but I think that it's the same end goal, which is that once the animal is out of your purview, then you can continue forward. So I think building in those types of properties, that's sort of a key point of some of my work. I don't know if autonomous car companies are thinking about that, but I mean, there'll be a lot of animal activists that are upset if not, so.
Okay, I get to ask one from Stephanie. Thank you for again joining. Stephanie has been with this series since its very beginning. She asked about government role here. And so I'm going to pose a question a bit differently, Stephanie. If you were Queen, Professor, what would you do of government policies to help and steer self-driving systems?
So if I was, sorry, I think I missed that.
If you were queen of the country, if you could determine the laws of the country, what would happen?
Wow. What would I do? I think I would say at least 2 things. So one is, I would say there's a standardized driving test for autonomous vehicles that is automatically generated. It is not the same every time. Again, we can do that in simulations. We have these wonderful simulation environments. I can add a bunch of random obstacles. Again, similar to our driving tests. When I took my driving test, there were a bunch of cones. There was a construction zone. I was very freaked out. We're going to make autonomous vehicles do the same thing. I think the second thing is that no autonomous vehicle will be able to be on the road if it cannot defend itself and you could ask it questions. Not, it doesn't have to be, well, it won't be. It doesn't have to be sentient. It doesn't have to tell you stories and be creative, but it has to be able to tell you what it did and why. And in fact, like the question earlier, we have all the logs. They're stored in different places. We just need a way to maneuver it. And then, the third thing is I think we really have to think about, and there's a wonderful article by Rodney Brooks called, I think it's The Trouble with Self-Driving Cars as the People, or some variant of that talks about the fact that the big problem is not going to be when there are a ton of autonomous vehicles on the road. The problem is going to be our behaviors, and the interaction between people and autonomous vehicles is going to be very different. Like, are there going to be people that just stand in front of a self-driving car to make it not move so that you can reserve a parking spot for your self-driving car? So I think those are the main things I would do. But again, I think the really big thing is the testing. Like I said, I work on this. As far as I know, I don't think there's any testing for these cars to go on the roads. I think that they have a bunch of fans up in the government and they say, sure, go ahead. And I think we need better standards for that. If we have to take driving tests, so should the autonomous vehicles.
I think that is the perfect place to end up. We've still got a ton of open questions. I want to thank the audience for all the amazing questions. I wish we could stick around for another hour, but Leilani probably would like to get dinner. So I'm going to say goodbye and turn it over to David.
Yeah, please join me in applause for Professor Leilani Gilpin. I think we can all sleep better knowing that the mind and hard work of our fellow slug is making our future roads safer. So I want to thank you, Professor, for sharing your research with us this evening. Now, she has a wish. She supports the MESA engineering program, which stands for Mathematics, Engineering, Science Achievement, for students who are the first in their family to attend college, often arriving from under-resourced high schools. We encourage you, and you're going to find down in the chat box, you're going to find the link to this. We encourage you to make a gift to support this fund. A contribution link again is being put down at the bottom. I'm going to add another request, and that is those of you out in the crowd who work with or for car companies, and if you have a way to put our good professor in front of car companies, you would serve the nation well. So I also want to thank the staff of the Alumni Relations and Special Events Offices who organized this webinar. Thank you, Shana, Diana, Paulina, and Kristen. Also a thanks to April, who couldn't join us tonight, but is a co-organizer of this series. We'll be back in Monday in a month. Our next Slugs and Signs will be July 10th, and we'll feature Daryl Wong, Executive Director of the Center for Agroecology at UC Santa Cruz. The Center for Agroecology works to advance agroecology through experiential education, participatory research, agriculture extension, and public service. And over the past 50 years, you probably know what is the organic farm. That's certainly one of the major aspects. It is focused on improving organic farming practice and increasing the sustainability of local food systems. It is currently spearheading an initiative across the University of California system to improve undergraduate education in organic farming. Daryl Wong has been with the center since 2013. Previously, he co-owned and operated Freewheeling Farms, a 7-acre mixed vegetable operation that sold produce in San Francisco and Santa Cruz. In addition to his role at the center, Daryl studies organic no-till vegetable production. Okay, well, meanwhile, there are a few upcoming events that I'd like to bring to your attention. I'm going to start actually with an exciting program called the Return to the Redwoods. This is where you're going to gather your friends, bring them together, mark your calendar for August 18th to 20th. And the event welcomes alumni, friends, family back to the UCSC for a weekend of celebration, exploration, and an opportunity to relive the beauty of the campus. You can reserve an apartment or residence hall room on the campus and join us in the Redwoods for a weekend of reminiscing and making memories. Prior to that, on Tuesday, June 20th, you were invited to the Spotlight Santa Cruz event featuring UC Santa Cruz alumnus Amadeo Bachar at Little Shop of Horticulture. During this event, you will enjoy a private gallery show from the artist, an hour-long interactive watercolor workshop led by the artist, some small bites and drinks, all while building community with fellow slugs. Then on Saturday, June 24th, there is a 90-minute Younger Lagoon Reserve tour beginning at the Seymour Marine Discovery Center here in Santa Cruz. This is a behind-the-scenes tour of the Younger Lagoon Reserve, which is part of the UC Natural Reserve System. Come and see what scientists are doing to track local mammals, restore native habitats, and learn about the workings of one of California's rare coastal lagoons. Now, by the way, I think that there's a link down in the chat box for the sign up for the Return to the Redwoods. In any event, you can find it with other events at events.ucsc.edu. So on behalf of the UC Santa Cruz Alumni Association, thank you for joining us, and please come back on July 10th, 6:30 p.m. for our next virtual event. Thank you again.